Welcome, welcome everyone. This paper provides a practical implementation of ML solutions for real-life challenges in the renewable energy industry. Moreover, it shows how a combination of electrical engineering and computer science knowledge can help to minimize the costs in wind farms and advance sustainability. I am a data scientist with a background in environmental engineering. I'm currently working on a data science contract for an alternative energy startup. And this platform is AI Socratic Circles, pronounced ACE. It's a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host recorded talks like this, plus live discussion groups, and produce premium content in various subject areas. To see more, visit ai.science and log in to access slides from this and other sessions and a lot more content. Also, make sure to subscribe to our YouTube channel, ML Explained, to get notified about upcoming talks. Mostafa Saeidi, our guest here, is a freelance data scientist. He has worked at the Advanced Analytics Department of Power Factors LLC as a data scientist. He got his Master's of Science degree in Electrical Engineering from the University of Quebec. He's passionate about the implementation of ML techniques for solving renewable energy industry challenges. So without further ado, I'll let him take it away.
Thank you, Ian, for having me. In the upcoming 15 up to 20 minutes, I want to talk about my paper, which was entitled Wind Farm Generators Thermal Condition Monitoring Based on Long Short-Term Memory. This was a work in collaboration with Power Factors, University of Quebec, and NSERC, which they contributed a lot in this research. The other authors are Philip Cameron, Ambina Pascayman, and Professor Ambrish Chandra. The outline of my presentation is first an introduction, background, and motivation why we chose this topic and worked on that. And I discussed the objectives of this research and the methodology that we followed. After that, I talk about the machine learning model that we developed. And finally, I discussed the results and the conclusion from the work. First of all, I want to talk about the importance of wind power all over the world. Canada is ranked 7th by producing around 2% of total electricity production by the end of 2017. So Canada is among the top 10, and there are a lot of companies and industries that are working in optimizing the power plants in Canada. In terms of the wind power production and wind power capacity, Canada is ranked 9th by producing around 2% of the total capacity of wind power around the world. The other issue that we should focus on is the gradual increase in terms of the capacity of wind farm in Canada. You can see that there has been an increase over the years, and by the end of 2019, Canada had more than 13 gigawatts of wind power capacity. Also, another interesting figures that gives us an idea how dispersed is the wind power capacity in Canada is this graph, which tells us that Ontario and Quebec and Alberta are top 3 provinces in terms of wind power production. Our focus in this research was Quebec province, which had around 4 gigawatt of wind power production by the end of December 2019. The other issue is the number of wind turbines that is interesting to us, because we want to implement condition monitoring techniques on each of these turbines and get sure that they are operating well. So we should know that by the end of December 2019, Quebec had around 2,000 installed wind turbines, and Canada had around 7,000 installed wind turbines. We should know that most of these wind turbines were installed more than 10 years ago. So over the years, they need some maintenance, and the costs of operation and maintenance for these wind turbines are increasing gradually. If I want to bring some numbers, I can say that by the end of 2019, the operation and maintenance costs of wind farms in Canada was around $290 million. And it was anticipated in 2019 that by the end of 2020 it would be $450 million. We don't have the exact number for 2020 yet, but it shows that a huge increase in terms of the increase in operation and maintenance costs. So this is an interesting point for many engineering company to make an impact in order to reduce this cost. And so all of these numbers told us there's a big market here which many of the companies want to work on. Before working on wind farm, we should know what are the equipments installed in a wind farm that might be interesting in terms of the condition monitoring. We have the wind towers, the hub, the rotor, the generator, the power converters, and also we have several step-up transformers and the cables. And at the end, we have the main step-up transformer or the substation transformer, which connects the wind farm to the power grid or the utility level. For condition monitoring, we should focus on the common failures in a wind farm. For each of these equipment, I try to provide some common failures. For example, for generator, we have the overheating in the phases or the cables. We have the unbalanced phases issues. We have reactive power control and rotational speed and active power control as well. For power converter, we have the overheating in rectifiers and inverters and the issue of unstable grid frequency control. For transformers, we have also overheating in the phases and unbalanced phases. And the other important issue is the utility requirements that the utility in our case was Hydro-Quebec that forces wind farm to follow a structure for the delivered produced electricity to the grid in terms of the frequency, active power, reactive power, and other features. These are the main, this graph shows the main failures in a wind farm. You can see that generator is among top 5 failures in an onshore and offshore wind farms. That's why we focused on generators, and also we had some limitations on the data sets that we have to work on other equipments. And also the resolution of our data sets was another thing that forced us to work on the generators. I talk about the data set in a while. The research methodology that I tried to follow was first a literature review to know what are the common methods that are used by literature to detect anomaly in the system or try to predict a variable for condition monitoring. The next step was refining the raw data that Power Factors provided us by implementing some of the pre-processing techniques in order to make it prepared to be fed to our model. After that, we try to define a healthy region of operation and faulty region of operation by focusing on the standards and guidelines by the Hydro-Quebec and other standardization institution like IEC or IEEE. And final step was employing the machine learning model to detect the anomaly in the system and also predict some of the variables. Sorry. The first method that was used for the anomaly detection was spectral analysis. In this method, in this paper, they suggested that we can extract the frequency spectrum for stator current of generator. When we draw this spectrum, frequency spectrum, we can see that when there is a fault, for example, broken rotor bars, there would be a spike in some frequencies that shows that the problem is related to the broken rotor bars. In the other word, each of the failures have their own signature in terms of the increasing the frequency And by extracting the frequency spectrum, we can detect what type of fault is in the system. The other paper suggested that not only we can focus on the state of current frequency spectrum, we can also extract the frequency spectrum of active power, generated active power, and so it's the same thing. When there's a fault, there would be some spikes in the frequency spectrum. The other method is signal training, and the whole idea of this method is comparing the operation of one turbine with other turbines or the average of other turbines. For example, this paper discussed the temperature of one turbine with others. But I should mention that this method is not quite accurate because the location of each of the wind towers and equipments is very important when we want to detect there's a fault or not. For example, the altitude of the tower and also the wind speed of each tower is different from the other tower because sometimes it's 100 meters of distance between each tower. So in this method, we have a high rate of false alarms. We have a statistical analysis, which we basically extract the mean value and standard deviation for each signal. And we detect the failures in the system by we define some boundaries for a normal region of operation, which is typically 3 standard deviations. If the value exceeds this value, there might be chance of failure in the system. And the other method with signal processing techniques, which some of people developed Hilbert transform and wavelet transform. In our study, we focused on the windings of the generators and we try to focus on the temperature monitoring for them. The first step was to define overheating and the normal temperature. For that, we refer to the standards, which they suggested that there is a term for that, insulation class. Each of generator has an insulation class for the cables or the windings inside generators. This insulation class has a maximum allowable temperature, which is suggested by the standards. In our case study, the generator we were focusing on had insulation class F, which in the other word, the maximum allowable temperature for operation of these these generators were 155 degrees centigrade. The other issue that we had was we had around 40 features or 40 installed sensors in the wind farm. So that's a lot of features when we want to develop a model because it can cause a computational burden and also it can affect the accuracy of our model. So we try to use the correlation analysis in order to reduce the number of features in order to increase the accuracy and the speed of our model. For that, we focused on the Pearson correlation analysis to which you can see the mathematical equation for that to detect the most correlated features with the temperature of windings of generator. For models, we basically focused on 2 main models. One was multiple linear regression, which tries to extract a linear relationship between our input features and our target variable, which in our case is temperature of windings. It tries to it calculates the derivative of loss function in order to optimize, in order to find the optimal values of the weights. The other method was LSTM or long short-term memory, which is a part of the recurrent neural networks. It has different gates. We have 4 gates. We have input gate, output gate, and solid state update, which all of them try to try to make to decide which information is more important, and and tries to make the model, make the cell remember it for the next cell, and it will be passed on to the next cell. This is the mathematical representation of how this sigmoid function and tangent hyperbolic function affects the input data, which is usually the input data, the previous selected information, and we have the output at the end. This is how these LSTM cells are connected to each other back to back over the time. We have different, we try to develop different LSTM types. We have the stacked LSTM, which I discussed just now. We have bidirectional LSTM, which is typically a true stacked LSTM in opposite directions. One is uses the previous information for predicting the future information. The other is otherwise. We have also multivariate LSTM, which we use different input features to predict the target variable. About the data that we used, these data were gathered by SCADA systems. Typically, SCADA systems is some sensors installed in the wind farm. They gather the data, send it to PLC or RTUs. They send the gathered data to the main SCADA panel view, which will be ready for the operator to work on. It also can be manually inputs to the system as well. The data we were working was the resolution was the frequency of gathering was 10 minutes. So for every 10 minutes, we gathered all those 40 features, and we had around 2 years of data for our variables. For the hyper parameters, we worked on LSTM model. You can see that we defined the training data set ratio of 75%. We defined the time step of 12, which means it remembers 12 previous sample data. And I also recall that the sampling rate was 10 minutes. So it means the model remembers the last 2 hours of operation for the temperature of winding, which is quite a rational thing in our case study. We also used the Adam optimizer, and the loss function was minuscule error. The results for stacked LSTM. First of all, I should discuss that we defined 2 case studies. We worked in a wind farm which had around 73, as I remember correctly. It was 73 wind farms. We defined 2 case studies for that. Wind turbine number 7, which operates in a normal region. This is the graph shows the temperature of windings generator windings. You can see it is 100,000 samples data, and recalling that the sampling rate was 10 minutes, it shows nearly 2 years of operation for the generator. You can see there is 2 peaks and 2 dips, which shows 2 summers and 2 winters for this time series data set. In the right, there is wind turbine number 67, which is the faulty generator that we want to focus on. You can see after the 80,000 sample, there is an unknown increase in the temperature, which also you can see it increased up to 145 centigrade degree. We don't know what was the root cause and the root cause for this malfunction in the system, but we want to get sure that our model tried and had a good performance in predicting this failure in the system. So we developed a stacked LSTM first. You can see for the wind turbine number 7, it showed a good performance, and also for wind turbine number 67, it has an acceptable performance. But in terms of the accuracy of our model, we will discuss it in a bit by comparing it with other LSTMs and also multiple linear regression models. For bidirectional LSTM, we had the same issue, and the model perfectly tried to predict the model, the failure in the system. For multivariate LSTM, as I mentioned earlier, we had a problem of we had 40 features. So we tried to reduce it by first by using electrical engineering knowledge, by knowing that what variable is related to the temperature of generator winding. So we reduced that 40 feature into 7 feature, and after that we try to use correlation analysis to make it even less. You can see that the 7 selected features were nasal temperature. We have a generator stator current, produced active power, reactive power, rotational speed of generator, temperature of generator cooling system, generator stator voltage, and the target variable was temperature of generator windings. You can see the two-dimensional figures for these 7 selected feature. When how the intensity of the scatter plots shows that they have low correlations, and if they are following a linear plot, it means that they are highly correlated. This is a visualization for that, but for the mathematician and calculation, we have this value for the correlation, Pearson correlation analysis. You can see that, for example, for TGNC, which stands for the nasal temperature, and TGN, which stands for temperature of windings, have a highly correlated. So for multivariate LSTM, we try to plot the cooling system temperature, or TGNC. You can see it follows a similar pattern to our temperature of generator winding. So, which is basically a truthing based on the correlation analysis too. We also selected the active power based on the high correlation between these two features. And you can see for wind turbine number 7, the multivariate LSTM also showed a good performance in predicting the values. For wind turbine number 67, you can see there is also an sudden increase after 80,000 sample in the temperature of cooling system of the generator, which is quite a rational thing because they are located next to each other. And also, this is the generated active power of wind turbine number 67. So multivariate LSTM also showed an acceptable performance in predicting the values. So at the final step, we want to compare the performance of these models. You can see that stacked LSTM has a better performance than the other ones in case 1, and in case 2, we have the bidirectional LSTM, which has better performance, and also it has similar performance to stacked LSTM, but by far they have a better performance than multivariate LSTM and multiple linear regression, which is quite what we expected from our analysis, because when we work with stacked LSTM, the input was the input and output feature were the same. So the input and output features have correlation equal to 1. But for multivariate, the other features have less than 1 correlation values, and this one affects the performance of the model. As a conclusion, I can see that LSTMs clearly outperformed multiple linear regression models, and bidirectional LSTM had better performance Then the stacked LSTM in case number 2 for anomaly detection, which is a quite true thing because it's quite two LSTMs in different opposite directions. It provides better knowledge about the performance of our system. Multivariate LSTMs had an acceptable performance, but they still stacked and with bidirectional LSTM had better results. But multivariate LSTM can be used for root cause analysis, or when for occasions that we don't have the target variable, or there's been a problem in the sensors, we cannot capture new data from our target variable. And also, as a next step, they can be used for real-time applications as well. At the end, I want to thank Power Factors and NSERC and University of Quebec for providing the platform and the expertise that they shared with me. Thank you for your attention.
Thank you, Mustafa. I'll start off the questions, if you don't mind.
Sure, yeah.
So in the paper, you mentioned that you did multiple linear regression and various types of LSTMs. I'm wondering what made you select those specifically, and did you try out other models too in comparison?
When I started, I tried to define a base model, which I did that with multiple linear regression. And based on the power factors suggestion, the advanced analytics team suggested me that it might be interesting to work on RNNs. And I did a little study for that. I noticed that LSTMs, RNNs suffer from vanishing gradient problem, but LSTMs can solve this issue somehow by providing the four terms in the derivative structure. So if one of these terms tends to zero, we don't go to the vanishing gradient problem. That's why I chose LSTMs, and also I worked with that for predicting the stock market values, and they showed a good performance in handling the time series data sets. Yeah.
Got it. And then in the paper, you mentioned using analyzing the correlations and also using engineering knowledge for feature selection. Did you use both of those or only one of the two? And then did you look at other feature selection techniques as well?
Yeah, actually, I use both of them. As I mentioned, there were around 40, 40 features or 40 installed sensors in the system. And each of these sensors had more than 100,000 samples. So I couldn't use all of these for my models. I tried to reduce it. The first step was using my electrical engineering knowledge. For example, if we had the voltage at the substation level, and we also had the nacelle temperature. Uh, Based on the electrical knowledge, I knew that the voltage at the substation has a low correlation or has low impact on the generator temperature, or one generator temperature. So I try to exclude the features based on at the first step by using the electrical knowledge, and I reduced 40 to 7, and after that I used Pearson correlation analysis. But I haven't tried to work on, for example, other other dimensionality reduction such as PCA or other methods. But it might be a good idea to work on that for the future works.
Understood. And then did you try out or look at doing any time series forecasting, like predicting future values of wind farm temperatures based on the current ones and the current features?
Uh, Actually, my future work is now I'm trying to focus on developing a real-time model for that. That's tries to extending these OS teams as you saw during the presentation. It was mostly on anomaly detection, but for prediction, I'm trying to develop a model to predict that in the future works. Yeah.
Got it. And then what has Power Factor said so far about the model? What's been their feedback? Are is it them potentially, are they considering potentially putting it into production or anything like that? Or did they say?
Actually, when I handed the model over to them, it was when I finished my internship there. So I don't know what have they done with the model after that. But the feedback I got from them was very positive. They liked how they can use it because they were developing their software, their condition monitoring software for different equipments, and they were mostly focused on the rotors, the tower, and the mechanical aspects of condition monitoring, not the electrical side of the condition monitoring. So I know that they were very excited how they can use machine learning for the electrical equipment such as generator, power converter, substation, and transformer.
Got it. And then you mentioned we talked a little bit about next steps in terms of the real-time monitoring and prediction. Uh, are there any other next steps or further research that we haven't talked about that you would suggest or be interested in seeing?
Yeah, actually, one of the things that I get familiar with in the industry was root cause analysis. I know that many of the industry likes to work on this aspect as well because if you know what caused the failure in the system and how you can prevent that, I think it's a $1 million question if you know that answer. So root cause analysis is very important for the industry and for also for power factors. And I think the next step would be using classification or clustering to detect, for example, in this case study that we had, what caused this sudden increase in the temperature of generator. This is the next step for using machine learning techniques in order to know what other equipments or what other malfunction in the system caused this one. And this is interesting future work as well.
Got it. Thank you, Mostafa.
No worries.
I think that's all of our questions. So I really appreciate you coming here and presenting this work.
Thank you for having me.
Of course. And let's check the chat. Yeah, there's no other questions here in the chat. So, okay. Xiang, should we? All right. Bye, everyone. Thank you for attending. And this has been another ACE session. Please join and come to our other sessions.
Bye. Thank you.